Hey guys, so welcome back. Happy Friday. So what I want to do today is just do a little bit of an example, and this example is really going to be relevant for your homework exercise number 6. I'm going to do the Fourier transform on L1. You're looking at with something called the Volterra operator on L1, but it's a much easier operator. It's basically the antiderivative. Fourier transform's more difficult. But this is a great, the Fourier transform is something I want to use as kind of an underlying connection between all of our functional analysis. So what do we know about the Fourier transform? So what we did already is, what I'm going to do is I'm going to take an exponential function. Okay, so this is e to the 2 pi I k theta here. And theta actually is just a real number, but you can think of it as just living between 0 and 1. And we used the Hilbert space theory and the fact that these things are plainly orthonormal, and then with a little bit of help from the Stone-Weierstrass theorem, they're actually an orthonormal basis. And by the way, I'm typing up the notes from the Fourier transform stuff, and I'm going to try and include some of the details behind all of that. We went through it kind of quickly in class. I'm still assuming the Stone-Weierstrass theorem. I'm not going to put a proof of that. But given that, I'll show why these things are exponential basis. And so we use the fact that, these things are exponential basis and the Hilbert space theory, and we get that if I define the Fourier transform, so this is f hat of k, and this is f ek, and what it is f ek bar d theta over t, and by the way, t, remember, is r mod z, or you can think of it in the complex plane, but really it's just 0 or 1, okay? And so this is actually integral from 0 to 1 f theta e to the minus 2 pi I k theta. The minus comes from the fact that I'm doing the inner product, so I have to have a bar over that. And that is the Fourier transform. And so it takes an L2 function, that's the way we define it in terms of our Hilbert spaces, and it gives out a sequence. So this is for, let me write this over here, k and z. Okay. And our basic Hilbert space theory, and in particular something called Parsifal's, says that the L2 norm is preserved in terms of, the sequence of L2 coefficients. Okay. So this was the Hilbert space theory. This is actually what we call Parsifal's equality. Okay. And if you think about what that means, is if I view f, big F here, as a mapping from L2 of t to a sequence, what this thing means right here is that this map right here from little L2 to z is an isometry. It means it takes an L2 function to a little L2 sequence, and the norms, or the distances generated by the norms, are preserved. Moreover, this is one-to-one and onto, and so this is an isomorphism, and it's a linear map. Everything beautiful. All right, so what we're going to look at today is what happens when I switch this 2 to a 1. So on one hand, the Hilbert space theory makes everything nice for the Fourier transform. But on the other hand, somehow L1 is a little bit more of a natural domain for this Fourier transform. So let's take a look at that. Okay. So what if I take f in L1t? And recall what this means is it is a one periodic function that is integral, say, over 0, 1 with respect to Lebesgue measure. All right, and I define the Fourier transform in the same exact way. It's the integral from 0 to 1, e to the minus 2 pi I k theta d theta. This is my Fourier transform. I'm also going to still call this f hat of k. It's just a little bit easier thing. So what if I define this? Okay. Well, one thing you notice right away, oh, and by the way, this is okay. If you think about L2 theory, if we're on this set 0, 1, L2 is contained in L1. So what we're doing is we're actually enlarging the domain. Okay, and now it may not be as well behaved on this enlarged domain. Fine. Well, one thing you instantly notice is that since the exponentials are modulus 1, when I bring the modulus inside the integral, that exponential, and in particular the k, disappears. Okay? And this is what I mean, it's really natural low inequality here. And so this is the L1 norm of f. And now this thing over here does not depend on k, and so I can take the sup over all k, and in the natural inequality you've just gotten is that it maps L1 to little l infinity z. Okay, and even with norm 1, with if you want to write out the norms, this is little l infinity, and this is going to be less than L1 t. Okay, so fine, and that's just this inequality here taking the sup over k. Well, this is good and all, but this is actually a pretty big space, and actually we can do something better. So remember, for when I put 2 here, I get 2 here, and it's isometry. So it turns out that we can do a little bit better than this space if we're a little bit more careful. And then we actually get something kind of surprising when we use the open mapping theorem. So here's our main theorem. The Fourier transform f satisfies, it maps L1 into little c0 of z, and I'll talk about what that means in just a second, with norm 1, operator norm 1, and is injective but not surjective. Okay, not surjective. All right, so a little bit of a comparison here with what's going on L2. So when I shrink this space, then what happens? Well, it shrinks this space. It goes big L2, L2 of t to little L2 of z. If I'm in little L2 of z, certainly I decay off. Oh, by the way, what is this? This right here is what we call null sequences. And these are sequences that go to 0 as k runs out to infinity or minus infinity. And so basically you can write that concisely as the limit as k goes to plus or minus infinity, or you can do the absolute value of these things is equal to 0. Okay, so 1 over n, 1 over log n, you'd have to throw absolute value in there, but just stuff that decays out to 0, and it can decay as slowly as you want. Now the interesting thing here is it's not surjective, and actually this is a very, very deep problem in mathematics, is what is the range of the Fourier transform on L1? In other words, how fast must it decay? Can you get something that decays like 1 over k at infinity? The answer is yes. Can you get something that decays like 1 over square root k, etc.? I don't even know the answer to that question. So this is the actually characterizing what goes here, what's the exact range. Difficult problem. In fact, if you can figure out anything about that, let me know. We'll probably publish a PhD thesis in the Annals of Mathematics, and you'll get a postdoc at Princeton because it is that deep of a problem. All right, so all this is in the notes, but so if I did this video, it would take probably another 30-45 minutes. So I'm going to kind of pick and choose some things here. There's several things we need to show. First, operator norm 1. That's actually pretty easy. We've already proven it's less than or equal to 1. To show it equals 1, you just look at the sequence where it's got a 1 and the 0 slot and 0 everywhere else. You just look at the sequence, you just look at the function 1, and you can show that this happens. That's easy. What we need to do is we need to show actually that it lands in this smaller space, that it decays off to 0 as you run out, as you get k gets large either direction, and that it's injective and then not surjective. I'm not going to be able to prove all of those things, but I do want to show why it lands in this space. Okay? All right. And then obviously I want to show the big thing here is why it's not surjective. The injectivity actually is pretty complicated, but I'm going to leave that up to you in the notes. Okay. So, let's prove that F takes L1. Let's just prove this statement into little c0. In other words, the natural, if you just, like I said, if you just pull in the absolute values, you automatically get that it's living in its bounded sequence. Well, why is it, though, that it's going to 0? Okay, so first off, the trig polys are dense in continuous functions and hence dense in L1t, since this is less than the suit norm. And so, actually it's not quite that simple, but let me actually write this like so. This was a calculation I did back in the L2, and the same thing works in L1. Actually, it's even easier. And so here, g is a continuous function. And the idea here is, oh, and let me do one other thing. This you can dominate by the suit norm. So let me dominate that really quick. If you look back at the notes and what I'm about to upload for the Hilbert space stuff, it's got basically this calculation except for L2. But here's the idea. I want to show that the trig polys are dense in L1. So I want to make this thing small. Well, on one hand, I can get close to L1 functions with continuous functions. Okay, so this is as small as I want. And then on the other hand, I can get close to continuous functions in the L infinity norm with trig polys. This is the Stone-Weierstrass theorem. And so moral of the story is I can choose, given f, I can choose g so that this is less than epsilon. And then given that g, I can choose my trig poly p so that this is less than epsilon, and I get the whole thing is less than epsilon. Okay, so moral of the story is I can find a trig poly, given f in L1, I can find a trig poly that's close to f in the L1 norm. All right, so Now let epsilon be greater than 0, and f in L1 t. I want to show that the Fourier transform of f decays as k runs out to infinity. Well, get a trig poly. So those look like something like this. With f minus p d theta less than epsilon. Okay, so there we go. Now, notice I can compute the Fourier transform of trig poly is really easy. In fact, what is it? So the Fourier coefficients, or in other words, the Fourier transform, well, what they are is I integrate against, say, an EJ. Okay, and let me actually change the index of notation just so we don't get confused here. Okay, and what this is going to do when so I integrate this against an EK, an e to the minus k technically. Well, what's going to happen is, by the orthogonality of the e's, when I distribute through the integral, I'm going to get a bunch of zeros except for the one that matches up with whatever coefficient. And so, in other words, I get AK, and this is if k is less than or equal to n, and then if k is bigger than n, I get 0, because by orthogonality, all of these will integrate to 0. Okay. All right, so remember, what do we want to show? We want to show that the Fourier coefficients of f go to 0 as k gets large. So let's take a look at that. So I've got my trig poly, I know its Fourier coefficients, and now I want to, all right, well, if k is greater than n, then p hat k is equal to 0. So what I can do is look at f hat k. I want to make these things small. Well, what is this equal to? This is equal to f theta e to the minus 2 pi I k theta d theta. And now what I'm going to do is I'm going to add in 0. I'm going to add in the pk's. And what this is equal to is f theta minus p of theta e to the minus 2 pi I k theta d theta, like so. All right, so remember what this is right here, this piece right here, it's just zeros. It's pk of 0 if you look at the definition. All right, and now, and this is only because k is greater than n. It's greater than the degree of the trig polynomial, which approximates f. Now pull the absolute values in, and you get this, which by our choice of p was less than epsilon. In other words, what I've just shown is if f is in L1, then there exists a capital N, such that when I take k either bigger than n or less than negative n, that f hat of k is less than epsilon. And this means that the Fourier transform maps into little c0. In other words, it goes to 0 as k runs out to infinity or k runs out to negative infinity. All right. So that's the mapping into this guy part, okay? The one-to-one is actually quite technical, and you're going to have to look at the notes for it. It also uses the density of the trig polys. Roughly speaking, let me just give you a kind of a sketch of the one-to-one. So the sketch of f is 1 to 1. So the idea here is if f is 1 to 1, what does that mean? Let's try and prove that f is 1 to 1. what does that mean? Well, what it means, what I want to show is that if all of my Fourier coefficients, if all of these are 0, in other words, f, the Fourier transform, I take an L1 function and it maps onto the 0 sequence. So this is for all k. Then I want to infer that actually my f function in L1 is 0. Well, if you just look at this, what I can do is just a little bootleg. I can get f here, and now if I add any finite linear combination of these guys, I get 0 for any trig polynomial. All right, and now I use the density of the trig polynomials in the continuous function, and I get that when I integrate it, I get 0 for any continuous function. Okay, you basically take a limit of these guys, and you can show that limit exists. I do it carefully. And then from there, you approximate an interval, say, to a to b, by a continuous function, and that's not too bad. I get 0 for any a and b. And that does it. Now what you get is that actually that it's 0. You can approximate any Lebesgue measurable set by a finite union of intervals, and then basically that you get it. It works for any measurable set, and once you have that, this is 0 for any measurable set, that means that f is 0 almost everywhere. So this is what some people call a bootstrap procedure. If you assume this, just it's 0, again, integration against any exponential, then you get it against any trig polynomial, you use the density of those guys, get against any continuous function, use the fact that you can approximate a step function with a continuous function, you get against any interval, any measurable set, and then that's going to imply that f is 0 almost everywhere. All right, look through the details. I actually think I did a little bit different. I think I use the L1, the fact that when you do the antiderivative L1 function, you can differentiate it, but it basically boils down to the same thing. Okay, so let's talk about why is f not onto. So this is the fun part that uses the open mapping. Is not onto. And this is going to use the open mapping theorem. All right. Well, first off, consider what we call the Dirichlet kernel. And so this guy is dn theta like this. Okay? So, first off, this thing is a trig polynomial. It's a trig polynomial, and all of its coefficients are equal to 1. Okay? Usually a trig polynomial would have like an AK there. All right? Now, that means I can easily compute its Fourier coefficients. So if I look at the hat, which means I integrate this guy, I should use a j here, but I integrate this guy against an exponential. Well, what happens is if the k's don't match up, then it's 0. If they do match up, I get 1, and so this is equal to 1. This is the same calculation I did earlier And so in other words, what's its Fourier transform look like? So remember, Fourier transforms, they take an L1 function. By the way, this is an L1 function. Why? It's bounded. It's an L infinity function. It's continuous. But if I just pull the absolute values in, it's less than, its L infinity norm is less than n. No, scratch that. 2n plus 1, because it's a minus. Okay, which is bounded. So it's in L1. And so what this thing looks like is, here's my n, here's my minus n. Its Fourier are these guys. Remember, Fourier is the sequence, and they're just a sequence of ones. Okay? And by the way, let me just get this on the scoreboard. dn is in L1 of t. It's one periodic, and it's, for instance, bounded. However, it's got an interesting form in that for each fixed n, it's in L1 of t. But what happens when n goes to infinity is bad. And so what we need to do is get a little bit better idea of what's going on. Well, let's take a look here. Let me write this out like so. So this is e to the negative 2 pi I n theta plus I n minus 1 theta plus e to the 2 pi I n theta. So notice it starts at minus n and goes, add them all the way up to plus n. So what I'm going to do is just take and multiply this thing by e to the 2 pi I theta. And by the way, all I'm doing here is just, this is just a little trick. This is actually a geometric series. This is just a little trick used to some geometric series. And what I'm doing is shifting things. So if I do this, when I multiply this in, what I get is e to the minus 2 pi I n minus 1 theta plus e to the 2 pi I n plus 1. I pick up an extra. Okay, so multiplying this just shifts the index. And now if I take and I subtract this one from here, well, what happens is all of these ones are going to cancel. And so what I get is e to the 2 pi I theta dn theta minus dn theta. What happens is that term does not cancel. And likewise on this guy's end, when I subtract that term, does not cancel. Let me make sure I've got that right. So e to the minus 2 pi I n theta. That's what I get. Yeah, all the middle stuff cancels, etc. Okay, so let's continue on with this up here. And so what I get if I factor out my dn theta from that, I get e to the 2 pi I theta minus 1 equals e 2 pi I n plus 1 theta minus e minus 2 pi I n theta. Okay? And if I divide both sides of this, I get a nicer formula, still not great, but a nicer formula for the Dirichlet kernel in particular. But I'm just going to be a little sloppy here and erase this. Okay. And by the way, all this is, guys, is this is just the familiar formula you learned. It's a version of the familiar formula you learned here of that. Okay, that's really all. And this is something you do back in Calc 2 when you're doing geometric series. Okay. So let's play around with this a little bit more. Write that down here. I'm going to multiply by an e to the minus pi I theta on numerator and denominator. And what's going to happen is I'm going to get an e to the pi I 2n plus 1 theta and e to the minus pi I 2n plus 1 theta and e to the pi I theta minus e to the minus pi I theta. Okay, you can think of this several ways, but multiplying by, let me write it here, multiplying by an e to the minus I, e to the minus pi I theta. Okay, you do that, which is equal to 1. This is what you get. And the magic trick I've done here is I've made these things line up except for the minus sign at both top and bottom. And now if you write out what this thing is equal to in terms of its trig function, so this is the cosine and a sine, the cosines cancel and you get a 2i sine pi 2n plus 1 theta, and down here you get a similar thing, sine pi theta. And again, times 2i's, those cancel out, and so you get this, I love this formula. This is the formula for the Dirichlet kernel. So the Dirichlet kernel is actually, it's the sum of all these exponentials, but the way you sum it up, it's this beautiful real function. And you can graph this thing out, what it looks like. And then as n gets bigger, these peaks and oscillations kind of go up. Okay. So that's a nice formula. Let me write this right here because we're going to need it later. So this is the derivation of this formula. Sine pi 2n plus 1 theta over sine pi theta. Okay, well, now we've got trouble because dny is an L1 is not an L1 as n runs out to infinity. So let's calculate its L1 norm. So what is this equal to? Well, one thing, sine of pi theta is positive for pi theta between 0 and 1, so I don't even have to write the absolute value. This thing is not positive because it oscillates a lot. It's got a bigger period. Okay. And so again, I didn't write the absolute value in the denominator because this is a non-negative function. And moreover, sine phi is less than or equal to phi. Phi is positive, and so this is greater than or equal to 1 over pi, from 0 to 1, sine pi 2n plus 1 theta over theta d theta. And now what I can do is I can just make a little substitution here. T equals pi 2n plus 1 theta. And then easily dt over t is d theta over theta. And when theta is 0, t is 0. When theta is 1, t is pi 2n. And so this becomes 1 over pi, sorry, 2n plus 1 right there. Absolute value of sine of t dt dt. And now, if you haven't done this calculation, go ahead and look at the notes, but this integral is divergent. As n runs out to infinity, you basically get the L1 norm of sine t over t on 0 to infinity. It's not an L1, and you can prove that it diverges. Basically, this acts like the partial sums of the harmonic series. You can actually prove that pretty easily. Look in the notes. But the key thing here is this goes to infinity as n runs out to infinity. And that's a problem. Okay? And so, moral of the story here, I'll let you guys work through the rest of this or look in the notes. And by the way, there's probably other ways to do this. If you think back to actually the last homework problem with the exponentials, that would actually apply here. You prove that the L1 norm of something like trig poly with coefficients 1 or plus or minus 1 is greater than 1. I think if you're a little bit more careful in that estimate, you can prove that they go to infinity. But anyway, key thing is that this L1 goes to infinity. It's an L1, it's finite for each n, but as n runs out to infinity, we've got a problem. Okay, now, why? So finally, we'll finish it up. Let me see how much time I have. So finally, we'll finish it up. Why is f not onto C0, Z? Okay, so the reason is suppose not, suppose so. So suppose f is onto C0Z, then f inverse is a bounded function, or sorry, it's a bounded operator by the open mapping theorem. But then f inverse dn hat will be dn. So what we have is that dn in L1 is equal to f inverse. By the way, f inverse exists if we're assuming it's onto, because it's only 1 to 1. dn hat L1. If it were a bounded operator, there would be a C there, such that this thing's infinity norm. And by the way, we already calculated the Fourier coefficients. They're 1 between negative n and n. In particular, their sup is 1. So this is equal to 1. And so anyway, that's bounded by a constant C, but that is a problem over here because this side goes to infinity. This is a contradiction. Can't happen. Fourier transform is not onto this space. All right, so have a good weekend, everyone, and I'll be back on Monday.